Now, what is shear flow in a fillet weld? Because here generally we will concentrate our study more related to fillet weld, this you should keep it in mind. So, in fillet weld what is throat area? First of all we need to know, because throat area means you can say this is our throat thickness T. So, if this throat thickness and if there is a well length L, let us sort of on this side there is a well length, at this side there is a well length L1, and this side also, both side if it is welding is there, this is let us also L1. Okay. So, here total length of the weld will be, if it is both side, total length of the weld will be, always you should keep it in mind, L1 plus L1, that means you can say 2 L1. So, what is throat cross sectional area? Throat cross sectional area will be throat thickness into length of the weld, that is generally here it is written. So, throat cross sectional area AB you can write as throat thickness T into total length of the weld. So, throat thickness T in terms of leg length you can write as, if this angle, let us consider here we are considering angle between two part is varying within this 60 to 90 degree, let us perpendicular two pieces, here you see this two faces angle is 90 degree. So, that is why here we will consider 0.70, this we will consider for rest of the study. We will consider our two specimen, that means flange and wave, which are perpendicular to each other. Okay. That is why we will consider this value, okay, 0.707. So, T you can write as 0.707 into W is the leg length. So, here W equal to your leg length, this you should keep it in mind. So, your throat area will be T into L. So, in terms of leg length there will be a factor this. Now, what is shear flow? Generally this shear flow is a very important parameters you can say, or it is a very important quantity you can say. It is generally used to determine the size of the weld. Generally shear flow is the shear stress at throat cross section, whatever the shear stress at throat cross section will be there, that shear stress into throat thickness is known as, you can say, shear flow Q. So, this is Q, I will represent as shear flow. Its unit is Newton per millimeter, or you can say its unit is generally you can say KSI into inch. Okay. These two units generally we will show you in this study, because according to United States customary unit, so USCI, this is called United States customary unit, you know this thing. So, they are generally use pound, inch, this types of unit they are use. So, KSI means you know KSI, you know these things, that is generally known as kilo pounds per square inch. Okay. So, here generally we will use pounds, here you can say Kp into inch, this you should, or KSI means kilo pounds per square inch. Okay. Kp means kilo pound, let us, or pound per inch also you can say. So, how this shear flow quantity is calculated, that little bit I am just showing here. Let us consider in shear, or you can say in throat area, let us consider the shear force in throat cross sectional area. Let us consider throat cross sectional area equal to V. So, what should be the, if the shear force is V, then what should be shear stress at the throat cross sectional area? This will be, you can say, shear force divided by throat cross sectional area AV you can write, this you can write as V by AV already I have shown you, throat thickness into length of the total length of the weld. Always if one side if the weld will be there will be L equal to only L1, if both side welding will be there then L equal to 2 L1, this I have already shown you, you see. So, here Q you can write as tau into that dimensional length, or you can say throat thickness tau into T. So, this will be you can say V by T into L into T. So, T will be cancelled out. So, this will be you can say shear force divided by L. So, this is called you see this is generally called as shear flow. So, this quantity is very important quantity for this design and analysis procedure. So, you got the idea what is shear flow, because this shear flow will calculate for all the direction of a welded structure. So, from there we will find out what is the maximum shear flow you can say of that what is the maximum resultant shear flow of that welded structure. Based on this maximum resultant shear flow, generally we will decide whether that welded joint is sufficient to sustain that load or not. So, for that generally this allowable strength design generally developed by what AISC, that is called American Institute of Steel Construction. Generally they generally term a quantity they that is called ASD, that is called allowable strength design. This allowable strength design generally they design based on strength of the electrode material which generally we use to do the welding. How it is, everything in details I will discuss in subsequent slide. So, we have already idea on electrode specification, because according to American Welding Society I have already shown you that what is the specification of a electrode. There we have already shown. Generally in case of industrial application we use very important two different electrode, one is called E60 and rest of the term I am not writing, and another one is called E70, rest other terms also are there, only I am just writing this you can say strength of the electrode. These two types of electrode have a popular application in the field of you can say steel construction. The generally this 60 is represent KSI, that means kilo pound per square inch, and this 70 also have a unit KSI. If this is this if we will convert into megapascal, this 60 will be generally 414 MPa and this 72 will be generally just proportion of that. Okay, that is you can calculate this thing, some just I am just showing 414 into 70 divided by 60, this way you can calculate. So, what should be the MPa, you can calculate this. Okay. Now, KSI generally popularly used by what I have already told you, United States Customary Unit, USCI unit, and this MPa unit generally used by International System of Unit or SI unit. Okay. This USCI unit also I will show, and this SI unit also I will discuss in this topics. Okay. So, here one things you should keep it in mind, generally according to this AISC ASD, I have already told you what is ASD. ASD means allowable strength design, AISC means according to American Institute of Steel Construction, this you should keep it in mind. So, according to this generally they told that okay, this tau max or you can say tau allowable should be equal to 0.3 times of FU. What is FU? this Fu is generally called this 60, whatever the electrode minimum tensile strength is there, this is generally called Fu. So, this is also called as Fu, this you should keep it in mind. So, allowable strength or you can say tau max, this both are same, this is generally considered there. From there generally what we can get? We can get a factor of safety. We know factor of safety equal to, that means divided by allowable stress of the material. Okay. So, from here generally we can get a factor of safety based on this standard, you can write as 3.33 divided by tau max or tau allowable, whatever it is that we can get. Okay. This you should keep it in mind, that things already here it is written. So, what is factor of safety here? We are getting Fu by tau max. What is Fu? Fu already I have explained, that in case of electrode, whatever the minimum tensile strength of the electrode is there, that is generally considered as what is called Fu. And what is tau max? Tau max is tau allowable, you can say. Now, according to, you see, now what happens here, I am just comparing the difference between ASD AISC standard and our mechanical engineering design standard. Generally what we used to do in case of mechanical engineering standard, we generally used to find out what is this tau max value based on some yield criteria, correct. Like in mechanical engineering approach, what we used to generally use for finding out the, you can say, design or tau max value allowable stress, generally here we use one basis yield criteria, or this is also called maximum distortion energy criteria, Okay. Generally based on these two criteria, how the factor of safety generally we are getting, that first of all I will discuss. After that actually I will show you why we are not using here according to mechanical engineering standard, that also I will discuss. Why we are generally we used to follow this American Institute of Steel Construction standard for finding out this allowable stress. Why? This I will just discuss. So, according to American standard of steel construction AISC ASD, generally what we can get, tau max you can get as 0.3 into Fu for a electrode. Let us this electrode, I am considering first one types of electrode, that is let us E60 electrode. This E60 have a Fu value is 60 KSI, or you can say this is equal to, you can say 414 MPa. So, according to, this is according to what? This is according to AISC criteria, tau max you are getting an 124. How? Already I have shown you, that is generally 0.3 into Fu, that is 0.3 into 414, you are getting as, you can get a value of this. Now, while we will use mechanical engineering approach, where generally we use one basis yield criteria, there we know generally tau max is equal to, you can write as you can say tau due to yield divided by factor of safety. So, tau due to yield, that means shear stress at yield point, or this is tau max, or also this is also called tau allowable stress. Tau allowable equal to tau max is equal to your tau yield divided by factor of safety. Okay. So, this tau yield, what is the value of these things, that I am going to show. So, tau yield generally you can get in case of plane stress condition, that is actually 0.577 into yield stress due to tension, yield stress due to tension divided by factor of safety n. So, this you should keep it in mind. So, there here this 0.577 into this sigma yield, generally here already is written yield stress of that electrode material have a value of generally 345. So, into 345 divided by you can say n. So, these are the tau max generally you can get based on what? This tau max you can get based on mechanical engineering approach. Okay. Now, how this 0.77 sigma yield due to tension is coming, this sigma yield value, this tau yield value, that little bit I am just discussing here. So, in case of plane stress condition, we can say there will be sigma 3 component, that means principal stress sigma 3 component will be 0, that you can say. So, according to the von Mises or maximum distortion energy criteria, what are the formula you know? You know half of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. This is equal to our yield in tension, yield stress in tension. These are the things we know. In case of plane stress condition, this will be, you can write as half into just sigma 3 you put 0. So, here you will get 2 sigma 1 square plus 2 sigma 2 square minus 2 sigma 1 sigma 2. This value generally will get. So, this will be equal to your, you can say sigma y t. Okay. So, this will give us a value, this I am just directly writing these things, then it will be more clear to you. Okay. This you can write as sigma y t square, you can write as sigma 1 square. This actually in case of plane stress condition and you can say let us pure shear condition, pure shear condition. So, first of all plane stress condition I am writing, then it will be more clear to you. So, plane stress condition generally this will be sigma 1 square minus plus sigma 2 square minus sigma 1 sigma 2. Okay. Now, if it is a pure shear case, because here generally failure is occurred due to what it is called shearing at throat area, that is why we need to consider pure shear. So, in case of pure shear, here I am writing in case of pure shear case, in case of pure shear condition, always you should keep it in mind, here generally sigma 1 is equal to, you can say sigma minus sigma 2 is equal to, you can write as tau. Here will be shear stress only, what I am telling, understand, because there will be generally a state of stress. If you just write, you will get generally you can say there will be pure shear, this is a pure shear case. This is pure shear case. Here you can write sigma 1 is equal to minus sigma 2 is equal to tau. So, if we put this value in this equation number 1, so what are the things we are getting? So, here we are getting sigma y t square is equal to, we can write as tau square plus tau square plus, you can say y plus, there will be 1 plus and minus. So, here I am writing sigma 1 is let us tau and another one will be your minus tau. So, this will be given as 3 tau square. Okay. Now, so from here generally this tau, this you will get as sigma y t divided by root 3. So, what is sigma y t divided by root 3? So, tau you can get as 0.577 into sigma y t. So, how it is coming? You got the idea. So, in case of pure shear case generally tau value we are getting as, that means you can say tau at yield point, tau at yield, the shear at yield y. So, that thing generally here we put in this equation, here you can see in this equation we put, that is F y means your you can say yield stress, you can say this yield stress due to tension, this is you can say sigma y t, this you should keep it in mind F y. This sigma y t value I put here 345, already I have told you yield stress due to tension 345. So, this will give us a value of 199 divided by n. So, you see based on this equation number, this is equation number 2 and this is equation number 3. So, based on this equation number 2 you got generally tau max is equal to, or whereas according to mechanical standard, mechanical design standard, what you get, tau max or allowable stress you get as 199 divided by n. So, from here you can, if you just equate this two equation 2 and 3, from this two equation if you equate this thing you can write as 124 equal to 199 by n. So, your n will be equal to your 124 199 divided by 124, 199 divided by 124, this will give us a value which is 1.56. So, according to mechanical standard generally we are getting a n value, factor of safety value which is less than you can say 3.33, that means it is more conservative. So, to be in safe side, it is that side, to be in safe side it is better to use this higher factor of safety which generally used by what, AISC ASD standard, American Institute of Steel Construction ASD standard, whatever the n value generally there we get, that is actually 3.33, whereas according to mechanical engineering approach generally we are getting a less value of factor of safety. That is why to be in safe side it is better to use higher factor of safety. That is why in our subsequent design and analysis of welded joint we will follow this AISC ASD standard, this you should keep it in mind. Now, so first of all you got the idea why we will use AISC ASD standard for allowable shear stress calculation. Now, we will go for discussing what is allowable shear flow. Allowable shear stress already I have shown. Now, allowable shear flow now I am going to discuss, because allowable shear stress is now known to you. What should be the allowable shear flow? That this allowable shear stress into throat thickness, that things only here it is discussed. Generally this for calculating this allowable shear flow, this concept generally was presented by Hall et al. In 1961, long back it was generally presented. Now, nowadays also this approach is very popular for well designed purpose. Okay. So, here already I have told you what is allowable shear stress, that is I have already Fu by n, because we will use ASD AISC standard. So, according to ASD AISC standard we know Fu equal to, this is called electrode minimum tensile strength. Okay, this you should keep it in mind, Fu. So, here Fu is more appropriate, that is why I have written here. Okay. Now, how to calculate this allowable shear flow? So, this allowable shear flow here I have written as Q allowable. So, I am writing allowable shear flow, that I will show you how to calculate this thing. So, allowable shear flow will be generally Q allowable, this will be equal to your tau allowable into you can say throat thickness. So, what is tau allowable? Tau allowable you can say I have already shown you Fu divided by N, here there will be T. Okay. Now, you see what is T? Fu divided by N, this T you can write as, in case of size of the weld 0.707, that leg length in the weld is this you can write. Okay. So, now for generally two different cases how to cash, I am just showing an example for E60 electrode, here generally Fu value is 60 KSI or 414 MPa. So, for this case according to United States USCS, United States Customary System, always you should keep it in mind. Here generally we use pounds, then you can say inch, pounds and second, this unit generally we use, and SI unit means International System of Unit. So, SI unit here generally we use, it is a metric system, you know this thing. Okay. So, here generally meter, kg and second, these are the things generally we use. So, for 60 rod, how this allowable shear flow is coming? This is actually kilo pounds, KIPS means kilo pound per inch, and this is generally this unit kilo Newton per millimeter. How it is coming? That little bit I am showing. So, you know Q allowable is equal to your Fu, that means 0.707 Fu W divided by N. Okay. Now, here if you use 707 into Fu, what is Fu means KSI. So, if you put here 60 into W divided by N, you will get a value which is similar to this. Okay. This you should keep it in mind, that is 42.4 divided by N, its unit is kilo pounds per inch. Okay. Now, according to SI unit, here generally kilo Newton per meter, this also I am just showing this calculation. So, here generally Fu equal to 414. So, here this standard I am just showing, Q allowable will be, because these are the things you need to know, 0.707, Fu is 414, this is W divided by N, this unit is what? Always you should keep it, this is Newton per millimeter. Now, once you convert this thing into kilo Newton, so this will give us a 293 W by N Newton per millimeter. So, once we convert this thing kilo Newton millimeter, then it will be 293 W by N kilo Newton millimeter. This you should keep it in mind. So, you see this is according to SI unit for E60 electrode. Now, for E70 electrode also I have shown what is use SCS and what is what it is called according to SI unit, what is Q allowable, that means allowable shear flow. Okay. Now, we will just discuss for a combined load how to find out this what it is called shear flow, that related things in details we will discuss. So, first of all we need to specify what should be our coordinate system. Here this is the coordinate system generally we will use for resultant shear flow calculation. So, how to find out this I will just discuss in detail. So, here just you see this x axis is perpendicular to the weld plane, this is your, you can see this weld plane is your. So, here I am writing yz plane is weld plane, or you can say this is also called shear plane, and this x axis is perpendicular to the weld plane, this you should keep it in mind. So, that is why here you whatever the force act along this x axis, this is called axial force, this is called axial force, this you should keep it in mind. And whatever the force act in y and z direction, this let us p y and p z, this will be generally shear force, this will be generally shear force. You see this is actually you can say normal to the weld, this is you can consider as normal force, and this p y and p z is called shear force. Apart from these things, generally this weld here generally it can be subjected to bending moment m z, and it can be subjected to torsional moment m x. Always you should keep it in mind, this is generally called torsional moment m t or torque T, and this moment m z is equal to your m b, this you should keep it in mind. So, here whatever the moment will be here, this is actually torque or torsional moment, and whatever the moment will be through this z axis, this will be generally you can say bending moment, or you can say this is also here it will be m z. Okay, this you should keep, here it is m x, this you should keep it in mind. So, this coordinate systems we got. Now, along these three coordinates x, y, z, we will find out what is the shear flow component generally along x axis, along y axis and along z axis. Let us along x axis, after a combine of loads along x axis, that let us consider the component of shear flow we got as q x, along y axis direction the component of shear flow we got as q y, and along z axis let us consider component of shear flow we get as q z. Now, based on this overall shear flow in three direction, we need to find out what is the resultant shear flow. So, this resultant shear flow how we can find out? By generally vector addition also you can say, that means magnitude of the force whatever the way we calculate. Similar way here also we can calculate q r is equal to a square root of q x square plus q y square plus q z square. So, similar to the equation used for determination of magnitude of a force, same things also we can use here, because if the component of the force is known, then what happens, resultant magnitude of the force generally square root of q, that means f x square plus f y square plus f z square. Similar way here also resultant shear flow q r we can calculate as this. Now, here one things you should keep it in mind, for a set of weld, first of all we need to find out what is the resultant shear flow. This resultant shear flow we need to compare with allowable shear flow. Okay. This ratio, if it is less than equal to 1, then our weld will be safe side. So, this resultant shear flow, whatever the things we are calculating, this resultant shear flow we should calculate based on maximum stress location, this you should keep it in mind. So, resultant shear flow we will calculate based on maximum stress location. So, at a maximum stress location, whatever the what it is called shear flow value we will get, based on that maximum shear flow resultant, we will compare whether this is exceeding this allowable shear flow or not. Whatever the allowable shear flow for different types of rod I have shown, that I have already shown in previous slide itself. So, we compare it. So, if it is less than equal to 1, then we will be in safe side. Okay. If it is greater than 1, then what happens? You need to redesign it, you need to recalculate your what is called dimension of the weld or structural components, material type, you need to change. What I am telling, and that related things I will discuss in next lecture, and I will solve some problem on what is called shear flow, based on shear flow how to design a welded structure. Okay. Thank you.